Hello, everyone. This is the carbon capture panel, and I would like to start off by introducing the panelists with just a quick name, background, and why you're interested in the subject. My name is Don Ritter, graduate of Marietta and SMU along the way. Spent 20 years with mobile, then 7 years in geomechanics, and then another 15 years or so running my own company. So I've been involved on the peripheral of injection, carbon injection, or CO2 injection, CO2 flooding. So I'm going to speak a little bit to that side of the business. Matt?
Good morning, everybody. My name is Matt Telfer. I'm a geologist. I've been working in the oil and gas business for about 45 years now. I graduated with a geology degree from Binghamton University, and I've spent most of my career between the Rockies and the Mid-Continent and down into Texas. We drilled a lot of Austin Chalk wells using horizontal drilling, advanced technologies in terms of getting deeper faster. So this led me along the way to work with one of my friends in developing a company called Renewable Energy Storage Company, looking at storing compressed air in salt caverns and generating electricity. So we'll be going into that a lot more.
Mark?
Thank you, Don. Again, my name is Mark Courtney. I am with a company called Chart Industries that focuses on cryogenics, and also with HOWDEN that focuses on air and gas handling in small, large specialty applications. So I'm a mechanical engineer by education, so I encourage all your engineering talents to be broad as you learn in this space: doctors, lawyers, engineers, and teachers. But with my engineering degree, I went into sales. So I've been into sales and marketing for about 40 years. And my specialty is large capital expenditure and engineered systems. So carbon capture, utilization, and storage was a natural fit for those of us that come from the oil and gas background. So again, thank you for having me here, and look forward to working with you.
I guess I'm last. Omar, Abou-Sayed. My background is a mechanical engineering degree from the University of Texas at Austin, and then I did an MBA from the Harvard Business School. I worked in upstream oil and gas as a facilities engineer, reservoir engineer, and an operations engineer before kind of getting a tap on the shoulder to go do some executive development for BP in London. Did my MBA, came back into chemicals, so I switched, worked in chemicals for a while, and then ended up in a series of smaller and smaller entrepreneurial ventures around clean tech, backed by private equity or as part of a private equity group. My interest, I had identified. I'm part of the generation that came into the economy. I graduated university in 98. My first internship in the oil and gas industry was 97, in the post-Kyoto Protocol era. And so climate change was something that we were taught in school. It wasn't a controversial, newfangled thing. And ultimately, my very first job at BP was to make the Gulf of Mexico compliant with the Kyoto Protocol, to reduce our emissions by 10% off a 1990 baseline. So climate has always been part of my career DNA. And as I matured and found ways I could take the best of oil and gas techniques and technology, and that, the core expertise, it's clear that those are the expertise that are needed to deliver a carbon-free world. And so I wanted to be part of that guard moving across.
Okay, great. So I'm going to kind of just kick it off with a little bit of intro comments. Greetings. I'm Don Ritter. I'll moderate today's discussion. Carbon capture, sequestration is one of the more important components of net zero at any day now or 2050. In fact, without it, we may never get there. In the last 20 years or so, we've only offset the fossil fuel use from about 86% to 82%. And that includes coal. Realistically, the amount of fossil fuel use will actually increase by about 2% a year for the next several years to keep up with the growing energy demand. The more wind and solar that we put into primary load, more coal and gas or nuclear we're going to need for security backup. So we have even more need to offset carbon via capture and sequestration. One of our keynote speakers earlier today, Chris Kendall, talked about blue oil, which is produced via CO2 injection and gives us a net zero or a net negative barrel of oil. The great hope is that this process plus direct air capture and sequestration or storage will become growing components of the energy mix and offset going forward. Blue oil is an easy offset, but the DAC, direct air capture, and other sequestration methods require a lot of energy in the process. The good news that it's scalable, bad news that it's expensive in this current environment. Luckily, we have several new technologies that may help us get there. Nuclear might be one of them that helps us with lowering the energy costs needed to make DAC work. So our panel today is going to cover some of these new technologies that may help. I will likely cover CO2 injection and the blue oil concept. Matt Telfer will cover storage options for turning gas into batteries, as well as storage for blue hydrogen. Mark Courtney is going to cover some of the regulatory challenges and general challenges to direct air capture, sequestration, industrial environments, and some other topics, including COP28. Omar Abou-Sayed is going to cover a novel approach to sequestering solid waste and wastewater into municipal environments. So we have these three new ways of looking at it. I'll go back to the blue oil concept. As a 40-year oil and gas guy, I've been involved in CO2, petroleum engineering applications. It was really kind of developed in the 60s and 70s. They were called CO2 floods then, and tertiary recovery, employed only after primary and secondary, which was usually water flood. Today, these are still the classic reservoirs that are available for this application, but now the planning brings CO2 in the field development area much earlier and with purpose. And injection wells are now more robust with special casing cement to protect against corrosion. Hence blue oil. It's basically injecting CO2 in the reservoir, repressurizing or displacing the oil normally produced under primary production. It's called blue oil because the net CO2 used to produce a barrel of oil sequestered more carbon than the primary barrel it produces, including the scope 2 and scope 3 emissions. This is a classic injection and production operation, and there are tax credits associated with this method. More of this is headed to the Gulf Coast, but we can't make every barrel of oil blue. We need some other methods. My next panelist, Matt Telfer, is going to talk about some of these storage methods that either use compressed flue or blue hydrogen as a source of potential energy and then released later as kinetic energy, sort of a big battery. Matt, why don't you introduce this concept a little more?
Okay, thank you. I'd like to share my screen. We can get there. We've got a short presentation. Okay. Okay, so technology that I've been working with involves the use of salt caverns. And a salt cavern is made in a formation like a salt dome, or you could have bedded salt, but it's made by dissolving the salt. So you basically push some, you pump fresh water down a well, it dissolves out the salt, and makes a cavern. And a lot of these you can think of are about the size of the Empire State Building, so they're huge. Typically, they're used to store natural gas, and they're already a critical component of our energy system. There are numerous salt caverns around the country that store natural gas during the summertime, and then we can use it during the wintertime. They can also be used to store hydrogen, and they can also be used to store air. So, from a geology standpoint, salt deposits are located all over the world. And what our job is basically to figure out where are the salt deposits in relation to the electric grid. And our company has developed a portfolio of projects that cover all the major U.S. electrical markets. Some of the ones that we're working on in particular that we're interested in are in the Gulf Coast. Here we have the intersection of ERCOT grid, of the grid that covers the southeastern part of the United States, and also various industrial usage, including upcoming hydrogen development. We also look, you can think about this in terms, here is Colorado. We're working on a project in Rush, Colorado that would be at the intersection of all the wind and solar projects that are coming in from the plains area into the Front Range. If we can store energy here and then release it to the Front Range when it's needed, it would be very valuable. So one of our things has been to marry up the geology with the grid. And we come up with a system that we call Earth Store. And Earth Store is basically taking electricity off the grid while the renewables are really pumping out the electricity. When you got the wind is cranking, the solar is shining, you got a lot of electricity and its excess is cheap. We can take that, run a compressor, pump air down into our salt cavern. Then when the electricity is needed at nighttime or when it's really cold, then we blow the air out and run a turbine which runs a generator and puts the electricity back into the grid. The system has one novel component to it, and that is that as we compress the air, we generate a lot of heat. So the heat from the compression is stored in concrete blocks. And then as the air is pushed out of the cavern, it runs back through the blocks, heats up, and then runs the generator. That eliminates any natural gas that has to be used for the generator itself. And in this way, the whole system is truly carbon-free. It's a carbon-free battery. It's, by the way, and it's grid scale. It stores a tremendous amount of energy, and our base plate system is 150 megawatts. Now, what's interesting about this type of a concept is if you get into an area that has a lot of salt, you can make numerous earth store systems that could wind up being the battery for an entire region. So our company has done two proposals so far. One was to Austin Energy, which Austin has a mandate to be 100% green within a few years. We did not get that. That went to a battery. And then we also did a proposal recently for Xcel Energy. We received a 1, 2, 3 designation, which meant that our technology was to be pushed forward through the process without delay. And while we didn't get selected in the first round, we were recommended for future discussions. And because the system is pretty complicated, because you've got to build a salt cavern, then you got to build the system. You know, they want more information about how we can hit the hurdles. Now, one thing that's really interesting to us, especially down in the Gulf Coast of Texas, is that there's a rapidly developing hydrogen story. Okay, producing hydrogen, is effectively energy storage in itself. You're taking electricity off the grid and you're doing either electrolysis or you're doing natural gas reforming and turning it into a substance that has energy. The question is what is green? Can you take the electricity just off the grid from a coal plant or something like that? Or can you prove that you're actually using green energy from renewables to make your hydrogen? So I came up with this little diagram here. And this will be pretty much my last slide. But if you can run your electrolysis plant to make your hydrogen off of solar, the sun would shine about 6 hours a day for your maximum amount of electricity. Well, for the other amounts of time, you need three more of the same solar arrays to generate the electricity you need, plus one more solar array to run the system. So for every nameplate amount of electricity you need for an electrolyzer, you need to back up with 5 units of solar. Wind is less because wind is probably blowing more often, but then you run out of wind for days at a time. So to get a true green hydrogen, you're going to need vast amounts of renewable energy. And just to put everything into perspective from my standpoint, it's been working on this for the past 5 years, a solution for climate change. We've seen the development of wind, we've seen the development of solar. To get those running, you need backup. When we had the cold snap down here in Texas a few years back, we found out we needed to stabilize the natural gas supply. We needed to make more natural gas-fired peakers. Instead of doing storage, Texas said, we're just going to make peakers. We need to have coal plants that have faster ramp-ups. And with any of these point sources of carbon, that could lead to carbon sequestration. We need batteries, we need pump hydro, we need compressed air, we need hydrogen for storage. We need grid build-out. There's massive project backups at local interconnections now. We need to really move everything through. We need massive amounts of charging stations for electrical vehicles. We need carbon sequestration to take care of any point sources of carbon, and we need more efficiency. So all those things that go into becoming green is very complicated. And the more that I've gotten into this, the more you realize that all these components have to work together. And it's going to take a lot of doing, a lot of engineering, a lot of financing, and a lot of work. So that's it for me.
Great, Matt. Can you tell me what you think maybe has got the best chance of catching on? Is it either the kind of battery solution with compressed air, or is it more on the hydrogen storage? And how are these competing against lithium battery systems that we're starting to see pop up, especially in Texas? I know they put together kind of battery, almost I won't say a landfill, but they spread boxes of batteries out and connect those to the grid when they need them.
Yes, when we started our project, lithium-ion batteries had not been utilized on a grid scale. So just in the last 5 years, lithium-ion batteries are very simple. They're ubiquitous. It's very difficult to compete with lithium-ion batteries at this point. Our system looks like it will be more efficient than lithium-ion batteries at a levelized cost of electricity. So we have a lot of things going for us, but to compete with lithium-ion batteries is very difficult right now.
Do you think the competition is going to change as the competition for lithium increases all over the world and its costs start to go up and up due to its scarcity? Do you think this might help bring this back into vogue?
I think that, well, first of all, for us, there are only two there are two plants that are actually running right now. One's in Germany and one's in Alabama. So we know that the technology can work. We have to really get it up to us. We have to put in a new one somewhere along the grid that would really prove that we can outcompete lithium-ion batteries. So that's our struggle. That's our hurdle as far as our company.
Okay, great. Probably time to move on to you as the director of carbon capture with Chart Industries, leader in the CO2 and clean energy marketplace. Can you give us an overview of carbon capture, some of the areas you're currently working, in particular some of those headwinds facing the industry, and how do we develop a workforce to decarbonize at full scale?
Don, thank you very much, and Matt, great presentation. I'm going to try to share my screen, and I didn't have a chance to do this pre-meeting, so I'm going to share my screen to help set the stage. So a little feedback would be appreciated. See how this looks.
Yeah, there.
And
just hit slideshow, and you're good.
So are we good to go?
Yeah.
Here at Chart Industries in HOWDEN, and frankly throughout many of our industry contacts and colleagues, we look at tackling carbon capture as just one of the many ways to reach our climate goals. And throughout this presentation, I'm just going to hit some of the highlights on where there are opportunities to not only reach our goals, but to address some of the future concerns that we have on timelines that are very long, from 2030 to 2050 to 2070. I'd like to leave you with a message that we know how to do this. As complicated as some of it is, it's something we've done for years. In fact, carbon capture has been utilized effectively in the oil and gas market to help us economically retrieve the energy that has helped to build our economies into where they are today. And that's a global comment. So with permission, I'm going to forward on here and show you some highlights regarding carbon capture, utilization, and storage. Of course, Chart is a global company, and what I want to do is start here. Carbon capture is really an application. It's not a market, and it applies across oil and gas. It applies cement and steel. And what you'll hear is carbon capture is required primarily in all the hard to abate technologies where there are high temperature vectors, wherever there's heat. Now, however we get the heat's another discussion, but wherever there's high heat in excess of 400 degrees and up, these hard to abate technologies, oil and gas, cement, iron and steel production, and other petrochemical facilities, until process technology changes, we have to recognize that these are difficult areas to abate and are contributors to our greenhouse gas emissions. And of course, we can service across all of these industries and do today with gas handling equipment, primarily very large fans, compressors, turbines, and cold boxes for cryogenic storage. This is where I wanted to stop and really spend the time in the discussion, and hopefully everybody can see this. Okay, Don, if I could just verify everybody can see this pictogram.
We see it.
Got it.
Fantastic. This is normally what I have up during a trade event so that people can stop by and discuss the entire value chain of post-combustion, and I'm hitting some highlights here, post-combustion carbon capture. And it looks a little bit like a maze, but it really isn't. So I'd like to just present it to you a little bit on how carbon capture mechanically works, and all the opportunities for improvements, for efficiencies, for scalability. Again, keeping in mind that we know how to do this. The focus of this particular conversation is on post-combustion. In other words, we've already burned the fuel that creates the challenge. And before I go through this maze, or it could appear to be a maze, the real issue is we have to adapt. And I think one of the questions that already came up is, how do we control pollution in third world countries? I'd like to introduce the ARC principle, where A stands for avoid, R stands for reduce, and C stands for capture. So here I kind of stand before all of you learning what carbon capture, utilization, storage looks like. And capture is just one of the pathways to help achieve our goals. First, we need to avoid burning the fossil fuels where we can, and this is where the green concept comes in with other technologies that require energy from other sources that are considered non-fossil fuel, be it wind or solar or energy storage. Those concepts fit the bill for green energy. And reduce, if we could just become more energy wise, and this is the challenge across the globe. And if you think about it regionally, United States is a developed area. Europe is developed. India, China, and some of the Indonesia regions, they have various degrees of development. But each region looks at their journey in decarbonization with respect to their own economy, with respect to their own life standards. So if there's a way to avoid burning fossil fuel or reduce it, I can tell you they're looking at it. There are already many boards and companies that are dedicated to globally address this. But the head start is in the United States, followed by Europe, and then the rest of the world. But when it comes to carbon capture, again, by region, what makes it exciting for us here in the United States, primarily as a leader in this, is the legislation that's supporting all of the tax credits that allow this pictogram to actually go into motion. That is the term we use, pencil out. The economics work with the support of the US government. There are other agencies around the world that are looking at this and supporting it similarly through private and government adventures. There's the EU Innovation Fund, which is making tremendous progress. You can't read a news article on LinkedIn about carbon capture today without seeing the progress that the EU's making. And then there are dedicated countries that say, our economy says we do have to burn coal for a while. This is how we have to build our economy. However, they're making the commitments to, okay, if we're going to burn fossil fuels, how do we make it net zero? And there are plans in place and projects throughout power generation, petrochemical, oil and gas that make this not just a discussion, but they're going into practice with real feed studies, that is front-end engineering and design studies. And there are commitments from governments and major industry players all over the world. And I've had the pleasure to work with most of them, so it's quite a joy. This pictogram looks simple, and it really is. And I think I'd like to simplify this for the sake of post-combustion. And if you can see my mouse, I wish I could turn it into a pointer. But
We can see it.
the mouse, thank you very much. The mouse starts this process, and this first bubble is the capture component. How do we capture it? You either capture it out of a stack, which means I found the source, the cement plant, the power plant, the steel plant, whatever it is, and there's truly a point source to capture the carbon out of the exhaust gas. That's point source capture. And we refer to that as source to sink. If we go all the way to the back end, there's a sequestration pile down here low in the lower right-hand corner. But point source capture is one way, and that's taking care of the things we couldn't avoid or the things we maybe could have reduced in a world that continually needs more resources. So we'll come back to that. But it is a technology called capture, and we know how to do it. The other one is direct air capture. Direct air capture, I attend these trade events, is sometimes referred to as the crazy cousin of direct air, of carbon capture. And that's because it needs green energy to really make an impact. It has two roles that can function simultaneously as direct air capture. Wherever you put it, it can take care of legacy emissions that are in the atmosphere causing some of our problems. In other words, what's happened over the last 50 industrial years, direct air capture can impact that at large scale. And then as you continue to operate them in our go forward mode, they can help also clean the atmosphere from emissions that are generated that are not captured at the point. And some of those could be agricultural, cows, dairy. There are so many other emitting CO2 sources that can't be point source captured. So direct air capture plays a role there. Again, to make it net zero and approach benefiting our carbon in the atmosphere, you need green energy. So everything that we just heard so far assumes that as these technologies develop and become deployed and located physically in places where that's feasible, direct air capture can play a role there. However, once it's captured, bubble number 1, we go to bubble number 2, and then ultimately down here to bubble 3 and 4. So I want to move through this swiftly. There are opportunities throughout this value chain for many, many manufacturers and engineering services to provide value. In here, there is an amine loop, which is a way of capturing and processing, in this case, CO2. And then you can capture it as a gas and say, all right, well, what am I going to do with it? Well, I may liquefy it, and now I have liquid ready for transportation and storage, because it's a whole lot easier to move liquid. Or it stays as a gas, and we have to find ways in close proximity to where that gas can be moved and ultimately go into sequestration, or can be used, which is the U in CCUS, effectively for enhanced oil recovery. And sometimes that has a negative connotation, but as long as we need oil and gas in our energy mix, it's best to find ways to do it more efficiently. And that's where carbon capture utilization comes in. The downside of that is if we capture everything we can up front here, and I'm saying everything required to keep us underneath our greenhouse goal, the Paris Climate Accord of 1.5 degrees Celsius rise, we're only going to use about 10% of that captured CO2. And that means use in cement, in oil recovery, food and beverage, agricultural, pharmaceutical. We're only going to need 10% of that as the market stands today. That means 90% of it, and we're talking gigatons, are destined for storage. So geology, geography, know-how, existing infrastructure plays such a huge role in the success of sequestration in the CCUS value chain. So much so that all the colleagues I work with start any project that's going to become viable, they start with storage. What are we going to do with it? And then you actually work backwards. So as long as you have a good place for storage or a good place for use, the rest of this front end is well known and understood. Currently, it's fairly expensive, and with the help in the United States of the IRA legislation passed last September, it helps the economics pay out not only to make the project start, but there are credits for up to 12 years after there's shovels in the ground and the project's actually operating. So that's the CCUS value chain. And boy, I'll tell you, I usually spend about 4 to 6 hours training folks on what this looks like, because every one of these little icons on the outside, which I wouldn't expect any of you to make out, are product opportunities for us as engineers and application engineers and people that are dedicated to make this entire value chain work. There are product opportunities for fans, compressors, turbines, steam recovery systems all throughout this value chain to make it cost effective. That's a lot, but I wanted to spend the majority of my time on this value chain. And Don, if you want to ask questions in regards to policy or any of that nature, I'd be glad to field those at this time.
Great, Mark. I think we've got one question that I'd like to propose. there's a thing called COP28, and essentially this is the climate change conference among nations that get together and try to decide, where do we need to go globally with climate change, and then it incorporates all the various parts of that, carbon capture and changing over to fuels, etc. I know that it's coming up in the next couple of weeks. They are supposedly focusing on the pre-2030 cuts in carbon emissions, and also the compensation for developing countries versus industrial countries, creating the climate crisis. First, how do you think this will play out? And secondly, they currently don't really hold carbon capture in high regard of being effective. From some of their statements that have come out of the committee. And I'll preface that with a graph I saw this morning that Chris had, and I don't know if it was metric tons, gigatons, whatever tons it is, it doesn't really matter. Currently, we are capturing about 40, I believe, through carbon capture process, and we need to 40 million, and we need to capture 6 billion by the time we can get to net zero. So there's a huge ramp. I think the comment was we're going to build a CCUS plant once a month for the next 20 years to get to this scale of removing carbon. So having said that, where do you think the COP28 is going to land?
No, great messaging there. And let's work backwards. COP28 is the next meeting. There's no question about that. But the transition of, I think, the forum of COP28 maybe even started, I'd say tangibly back in COP26, where the folks, I'll say 2-3 years before that at COP26, really we're still jumping off of what are we going to do and how are we going to deploy it to meet our targets of the Paris Climate Accord. They really were focused on this 1.5 degree temperature rise. And then COP27 moved to a different location. And this is where they started to talk about reparations and funding and, hey, we didn't cause this problem, so why do we have to pay for it in, proportion? So really they started to move into the political discussion and moving away from the technical feasibility of accomplishing our goals. So I think what we're going to see in COP28 is a return to, can we deploy at scale fast enough, and where will we do it? That will help identify who pays for it. But using standard Pareto thinking, you're going to want the biggest emitters to carry out the biggest change in their behaviors. So I think there's still going to be that kind of pressure. But as far as remedy to developing nations, I don't think they have a clear path yet. I read and listened on COP27 and some of the discussions, but it would take some global cooperation in a very difficult area that we haven't seen before. I think we're going to quietly recognize that we need fossil fuels for the near term, and your definition of near term may be different than most, but for the foreseeable future, we have to remember how do we avoid creating these emissions? How do we reduce them and ultimately capture them? So capture, like you said, there were some big capture projects that happened years ago, and they didn't deliver. And I'm not sure, I actually know why one of them didn't. They pinpointed it to a root cause, but we're learning. And in that learning, in that decade of learning, I think the reliability has improved, the engineering's improved. The whole value chain has been studying this for well over a decade. So I think there is room for not only confidence in CCUS delivering what it says it's going to, but to economically sign off on these projects and get some more examples under our belt besides all of the pilots that are in place right now. There are numerous pilots that are working to prove the point that CCUS does work. But boy, I'll tell you, COP28 may have a heavy dose of reparations, and this funding that they want to create that's a little bit beyond my scope to comment on, recognizing the geopolitical environment we're in today.
I'm not sure, but there's a difference between the industrial countries and the developing countries, and up to this point in time, I believe India and China have been kind of lumped into the developing country status, but I don't know if that's the case for the COP28 coming, and are they going to be on the receiving side of some of the funding, or are they back into the industrial side now, and especially with their use of coal? How do you think they're going to be viewed?
Yeah, great questions. I mean, here we're talking about world-changing scenarios, the largest population centers in the world, and they've been developing for a long time. Particularly China, you could say, is the number 2 or 1 economy, depending on how it's measured and what the data looks like. I think they'll have a hard time convincing anybody that they are on the developing side. And in India is surely has developing areas, but with its population and expertise in engineering and its hard to abate sectors that are feeding that economy, I think they're going to fall under the category of leading industrial countries that have admitted to continue to burn coal. So, again, it's, will they avoid burning coal and find better ways? Is there a commitment from these large companies and countries to avoid burning it or to reduce burning it? And capture is an interesting concept. We're talking about the CO2 molecule today, but 10, 15 years ago, we were talking about particulate, mercury, SOx, NOx. Now we're talking CO2. And I think China and India have committed to take care of their coal processes, at least through those areas. Now, to a greater degree compared to the US, perhaps. But I don't have enough data to support that. All I know is as they burn their coal, they definitely have the back-end air quality control systems to comply. So I would look for more compliance out of these growing economies because they want to do more. And to do more, they have to do it responsibly.
Last question there. We see that the U.S. is poised pretty well to kind of lead the world in carbon capture, and especially some of the projects that will be coming up on the Gulf Coast via Denbury and their recent merger with Exxon, which I think Chris actually announced today on his talk this morning. So we can only suck out so much, and the atmosphere is kind of a global thing. Do you see that the U.S. leading the path of taking out a lot of the legacy CO2? Is that going to play into how we stretch the funding around, or who is getting reparations? How do you see that?
Well, I think, yeah,
forward?
Great. And Chris is a wonderful leader. I've had the pleasure of meeting him down in Houston a few times. And I think what you're seeing is a consolidation of resources. We're recognizing that large integrated oil companies have some of the money or all of the money on their balance sheet to contribute and act responsibly while they're, I'll say, producing their art. And in that way, they're also making steep investments in similar companies. Chevron, this is all public knowledge, invested $300 million in one particular technology. And it's going to take more than just one technology. Direct air capture can be done many ways. So there are emerging, innovative, novel technologies coming out in the direct air space, direct air capture space, and not all of them are going to win. But the idea of strong chemistry, strong balance sheet, and investing in these novel technologies, it works. It works as long as we can start with storage. What are we going to do with it? So some of the economics has to stretch out across this entire value chain. The policy has to support it. The pipelines have to support it. The profitability has to support it for those that take the risk to make these enormous projects go forward. I mean, these are large. These are $1 billion, $2 billion a plant right now. They feel like large oil and gas projects. And I would say they are going to lead the way. The combination of our regulatory stance on supporting this through IRA and infrastructure bills leads the way. And then Europe to follow, and I think you're going to see private and public partnerships come out of China and India. And like I said, they already speak to them very clearly and have identified line of sight to massive projects to address this. Just a different timeline.
Great. I think now it's time that we move on to Omar. And Omar comes from a family of hydraulic fracturing and geomechanics experts. He's established himself in this arena as well, with this focus on sequestration of solid waste from water and sewage treatment plants. They're helping the communities sequester waste, provide offsets they can sell to the carbon market. Omar, can you elaborate on the process, how this can be scaled across the USA and other population-dense markets?
Yeah, and thanks for the intro. And Mark, I appreciate some of your comments about lots of ways to do direct air capture and some innovative technologies. I kind of want to, I'll walk through our version of one of those innovative technologies. So what we do at Vaulted, which is an affiliated company of Adventech Waste Management Services, which I founded in partnership with my father. And what we do is we take organic waste. This is waste that has carbon captured in it, and we sequester it underground. So, Mark was talking about direct air capture and flue gas and, talking really about capturing gaseous CO2 and transforming it into something that can either be used or sequestered. What we're doing is we're letting plants and vegetation do that work. So, ultimately there's CO2 in the atmosphere, it's captured by nature. And then there are products like grass that are used in the economy. You feed it to cattle. Cattle gets fed to a person. At the end, there's an organic waste that's left over. It might be sewage sludge. It might be manure. It might be lagoons from an animal feedlot. It might be anaerobic digestate, where they take manure and they run it through an anaerobic digester, let bacteria eat it and make methane. But in the end, you have a waste that still has carbon in it. Pulp and paper, sludges, et cetera, et cetera. I could go on. And that carbon, if left to its own devices, will decompose and return that carbon back to the atmosphere. Oftentimes in a worse form than it started. It will often return to the atmosphere as methane, which is 20 to 80 times worse for the climate than CO2. And so we take those organic wastes, we specialize in the really hard, nasty stuff, wet organic wastes that have lots of problems, pathogens, dissolved chemicals, pharmaceutical compounds in it, etc. And we sequester it underground. Now, it sounds very simple. Ultimately, and Don said it in his intro, I come from a line of scientists who, to a large part, invented and or really proved how hydraulic fracturing could be used to solve important problems in the oil and gas industry. We use hydraulic fracturing to part the rocks underground, which allows us to pump a slurry that contains this organic carbon into the earth, which would otherwise have just plugged your well up if you tried to inject, if you try to pump, you try to pump it without actually tearing the rock open to widen the aperture to let the solids flow in, you would just plug your well and you wouldn't have any storage capacity. So we take organic waste, we put it underground. About 3 tons of organic waste contain the same amount of carbon as 1 ton of CO2 would have contained. It's about 3-to-1 ratio. Interestingly, though, those same 3 tons of organic waste, if they are allowed to decompose and return in some to methane and some to CO2, those 3 tons of organic waste do 18 tons of CO2 impact on the climate because of the transformation into methane. And so we identified organic waste as a very strong way of economically removing carbon at scale. I mentioned we eliminate methane. We also deal with other types of pollution. 90% of sewage sludge worldwide is discharged raw into a waterway. And that's the same waterway where people may bathe in, they may baptize their children in, they may drink from globally across the world. So it's a real problem. It's a much bigger problem in other markets even than in the developed economies. I mentioned that we unlocked this advantage with patented slurry injection technology, but this is really this marriage of hydraulic fracturing married into a disposal well for the purpose of solids removal. It's very safe. We've done it for 30 plus years in the oil and gas industry. The first major project in oil and gas was one that my father led up with his colleagues at Arco Oil and Gas, now owned by BP, to remediate oil field waste that had been left on the surface of the North Slope in Alaska. And 20 years or so of waste being left at the surface, and then the EPA and the and state agencies, after the passage of the Clean Water Act, came and said, "Look, you can no longer do that, and in fact, you need to go and excavate the material you'd already put underground." My father at the time had been experimenting with using oil field waste like drill cuttings in lieu of proppant for stimulative hydraulic fracturing of oil wells, and had proven, he and his team, that you could put a lot of it underground. And so they repurposed that concept for the purpose of disposal of these wastes. One of his former colleagues took that same idea in the late 90s, early 2000s, to the city of Los Angeles, and proposed, why don't we take your sewage sludge, and instead of you expending hundreds of dollars a ton to dry it, to depathogenize it, and to drive it 150 miles to a farm to spread it on the ground, why don't we inject it for you? And I acquired that project for Adventech in 2016. We acquired it from my father's former colleague. And that really is the backbone of the new company, Vaulted, that we launched. One of the things that this technology does is, and Mark, you can comment, the cost today to directly capture a ton of CO2 from flue gas or ethanol or the atmosphere, it ranges, but it's in hundreds of dollars a ton. And in fact, some of the direct air capture to direct injection, CCS paths, they're selling their credits at $2,000 a ton of CO2, and they are saying they're still losing money at that price. So, we're talking about, can be quite expensive. Obviously, if you're doing it incident to producing oil and gas for EOR, you've got a different cost matrix. But these technologies are not inexpensive. When we do it, because we're not having to invest in the capture from the atmosphere, and because then we're doing very little processing, because we can actually inject the solids using pressure, our cost to sequester is super low. Our total costs are, lower than $50 per ton. And that is, the International Panel on Climate Change and most nation states have a goal of getting to $100 a ton of carbon removal. And we're already, our marginal costs, once our fixed costs are met, are already below that target. I talked about the Los Angeles facility. We take 20% of their sewage sludge every day, and in periods where they've needed us to, we've taken 100% of all the sewage generated from the city of Los Angeles, and we've injected it down one wellbore. And that wellbore has decades more capacity left, and we have 8 wells permitted at that site. We could literally take 100% of the sewage sludge from the city of LA for more than 100 years at a facility we built for less than $10 million, plus a few $2 million wellbores that we will drill over time. So, there are technology solutions that we can port out of the oil and gas industry like this, that are dramatically improvements over the current state of the art. And why it's important, look, there's a $100 billion market emerging for carbon dioxide removal. This is different than just abating emissions, one of the things we talk about is reduce, Mark talked about his ARC method, and reduction of emissions is a key part of it. But at the end of the day, there are these hard to abate sectors that will continue to emit. And for that, we need removal. For any of you out there who've heard of net zero means we reduce some of our emissions, and where we can't reduce them, we buy carbon removal products. So this carbon removal market is the net in net zero in that term. And, I won't get into too much of the sales speak, but ultimately, that's what we're trying to address and deliver, is low cost, high quality, permanent carbon removal, functionally using an oil and gas technology that was scaled by other investments. Sorry, I'll stop the share now and take any questions. But at the end of the day, one of the themes that I think some of you heard is the necessity or the likelihood that oil and gas is going to obviously continue for years. Time horizon, I think Mark said your time horizon may be different, but we have a moral imperative as engineers and scientists to A, preserve the habitability of our planet by avoiding the worst effects of climate change. But B, we have a moral imperative to do that as cheaply as possible and not waste money on science fair projects that are uneconomic. And number three, we also have an imperative to deliver abundant, low-cost energy to the people who are energy starved in the world, because there is no first world standard of living that can be achieved today without cheap energy. And so renewables are a key part of it. Solar is actually lower cost than fossil power in many instances. So there are times where zero carbon energy products are cheaper than their fossil equivalents. We really need to ask ourselves why we're not full-throatedly, wholeheartedly supporting nuclear deployment in emerging markets. But at the end of the day, we need to reduce carbon where we can. We need to do it as cheaply as possible, and we need to provide energy for those who need it. And I think you can only do that if you've got a way to remove the carbon that's going to come incident to fossil fuel use for at least the next 20 years.
Omar, thank you for that. That was very interesting. Can you go a little bit into the business model and any of the regulatory issues that you may have come across? Because I can see after everyone has figured out that LA is pumping everything down in one well, your phone is going to ring off the hook. So how do you approach that particular issue of getting it through a new municipality? And then, most of those people do not like drilling rigs, especially where the sewage plants are. So, you're talking about trying to get into an ultra dense population area, especially around the plants, to put this in place. And maybe you can give us a little on how that's coming together for other places.
Sure. So there's a lot of questions bundled in there: regulatory, public acceptance, and where we site it. Not every one of these facilities has to be sited inside a dense urban area. It is the least cost way to do it is to be incident and adjacent to the site where the organic waste is created. But look, organic waste is beyond sewage sludge. Organic waste